In the first 4 lectures, we learned how to assign a point group to a molecular shape. That point group is a summary of all of the symmetry elements of that molecule. And from that point group, we can construct a character table, which is a summary of all of the symmetry patterns. And those symmetry patterns are related to molecular motion, for example. And molecular motion has an energy signature. And if there's an energy signature, then we can detect it with spectroscopy. For example, you already know that we can detect vibrations and bending motions of molecules by infrared spectroscopy. One important stretching frequency we can detect by IR is this carbonyl here. And of course there are slight variations between ketones and aldehydes and amides, but they all have a strong band between, like, I want to say 1680 and maybe 1750 per centimeters. So that's just one example of how we can make use of these molecular vibrations. And they are, as I said, related to the symmetry. And so we have this stretching motion here where this carbonyl stretches up and down. But we also have other types of stretching and bending that's happening here. That can go this way, can go in and out. This is anti-symmetric stretching, and we have symmetric stretching. And the more elaborate your molecule, the more atoms you have, the more motion you can have. So let's take a look at all of the molecular motion that can occur for any molecules. There are 3 types of molecular motion: translations, which is movement in a straight line; rotations, which is the rotation of a molecule about an axis; and then the vibrations, which are the stretching and bending motions where the molecule stays put in place. And that's what we're interested in. So we're going to look at 2 examples: a bend in a linear molecule, and that's because linear molecules have 1 additional vibration if they have the same number of atoms. So we're going to come back to this slide in a minute. I want to go through all of the motion first. So translations are movement in a straight line, and so we have x, y, and z coordinates. So this water molecule can either move in the x direction here, or the y direction, or the z direction. So every molecule, whether it's linear or bent, has 3 translations. Let's keep that in mind. For rotations, we have 1 less rotation for linear molecules. And so if we put an x, y, z coordinate system on each of these molecules and go through the rotations, first of all, we have the y rotation. That's definitely a change in energy. We have for both molecules, and then if we do this about the z-axis, we also have, so we have 2 rotations. And then if we do the x-axis, now I couldn't make this molecule rotate about the x-axis the way it's shown here. So I did a little trick, but if any of you who are watching this know how to do that, I really would appreciate a note how to fix it, because what I'm about to show you is a little goofy. So I had to actually put the x-axis on the side so I can demonstrate that motion, right? So here we have the 2 molecules rotated 90 degrees, and now we're going to rotate them again about the x-axis. And so water clearly is moving about the x-axis. So anything that's not linear is going to have 3 rotations. But if we rotate the linear molecule, it basically stays put. There's no change. So linear molecules only have 2 rotations, which translates into this formula here, right? So we have we can calculate or predict or determine the number of vibrations by taking the number of atoms in a molecule, which is n here. So each of these has 3. So 3 times 3 gives me a total number of 9 motions. So each of these has 9 motions. Then the number 6 here for molecules that are not linear comes from the 3 rotations and the 3 vibrations. Sorry, 3 rotations, 3 translations, that's 6. So we end up with 3 different bending and stretching modes. And then for For linear molecules, we have 3 translations and 2 rotations, so we end up, as I said, with 1 additional stretching band or vibration. You all are well familiar with IR, but you may not have even heard of Raman. But the two are looking into the same energy signatures into the infrared region, but one complements the other. The IR looks into change in polarizability, whereas Raman looks into the change in electric dipoles. So sometimes you can see a band in IR but not in Raman, and vice versa. So if we now look at the 2 molecules I just showed you, we have symmetric stretching. Let's take a look at water here. We have symmetric stretching, and we have anti-symmetric stretching, and then we have bending. So those are the 3 modes. And the linear molecule has an additional bending mode here. It can bend in these 2 different fashions. So that's the summary of that. Earlier I mentioned that point groups have character tables and that we can construct one, and we will do so just so you understand where all of these symmetry patterns come from. But at the end of the day, you're going to have access to these character tables. I have one uploaded, and you can also just Google character tables point group and you will come up with them. So every point group here, and so this example is the D2D symmetry point group, right? And so the 2 molecules shown here are different, but they have the same symmetry. And all of the symmetry elements are listed here. So we have identity, of course, we have S4s, right? And so those S4s would be along here, right, where you can do a 4-fold rotation followed by a sigma h, right? And your sigma h would be here, and the only reason I mention it because this is one of the more complicated symmetry operations, and it doesn't hurt to bring it up and point it out again. So if you rotate any of these by 90 degrees and then reflect them through a mirror horizontally, you project the atom, again now the molecule, into itself. We also have several different C2s. We have perpendicular C2s, and we have those are tricky. I encourage you to look for them. And then we have, they call them sigma Ds in this case because there are mirror planes that are not necessarily vertical or perpendicular, so they call them sigma Ds. But it doesn't matter. We have mirror planes, we have 2-fold rotations, and we have an S4, and all of those symmetry operations are listed here. Then we have ones, usually 1s and -1s. And those are either, one is symmetrical with respect to an operation or a rotation or a translation, and -1 is anti-symmetric. So that's usually what it is, symmetric and anti-symmetric. And then over here we have, these are the IR and these are the Raman active symmetry patterns. So you can actually see the RZ here is the rotation about the Z-axis, the RX and RY, and then the X, Y, and Z are also representative of the translations. And so what that means is for the Z translation of a molecule in a D2D, we have a symmetry pattern that is symmetrical with respect to the identity. It's anti-symmetrical with respect to the S4, and then it's symmetrical and so on. If you have a plus, it's symmetrical with respect to that particular operation. And so that's just the initial overview of a character table. We'll come back to that. We'll look at what these are. These are called the Mulliken symbols, and so those are here. The mathematical operations are binary, and they are what this means is that if you have any of these symmetry patterns, they're going to be active if there is a character or if there is anything scribbled next to it. So here we have something written everywhere except for the A2. Anyway, let's come back to that later. Let's use a point group that's a little bit more user-friendly, like C2V. We know that C2V has 4 different symmetry elements, the identity, the C2, and 2 different sigma Vs. The C2 is right through the oxygen that dissects here, so that's important to know. And then we need to distinguish between the 2 vertical mirror planes if we assign an XYZ coordinate system. such as shown over here. The XZ would be perpendicular to the board, so that's important, and then the YZ would be in the plane of the board. And in order to come up with these symmetry patterns, there's a symmetry pattern for the X translation, the Y translation, the R rotation, and all those. And some of them overlap. But if we wanted to derive a character table or build one, we can assign vectors to each of the atoms. So let's say we want to know what the X translation is. So we put a vector on each atom and then perform each of those symmetry operations listed here, and you come up either with a symmetrical or an anti-symmetrical result, right? So if you perform an E in identity, nothing moves, you would have a positive value, so the character would be +1. And if you perform the C2, all of those vectors would point in the opposite direction, which would give you a -1. And then you would apply the 2 sigma v's, and you come up with a symmetry pattern that then would be representative of the X translation. So you don't have to do it for 3 vectors. You can just do it for a single vector on the central atom. It's going to make things much easier. And so we're going to do the X translation, the Y translation, and the Z translation. And then finally, we're going to do a moving vector around the RZ. So that's going to be the symmetry pattern for the rotation. And if we did that around the z-axis, if we did that for the y-axis, we would also come up with a symmetry pattern for that, but it would coincide with one of the others. By the way, this is always going to be a 4×4. If there are 4 symmetry operations, there are going to be 4 of these symmetry patterns. But that's so again, we don't have to use a vector here. We are using a p orbital with a positive and a negative end, and if the positive reflects into the negative, then we get a -1. And if the positive stays, or if the p orbital stays unchanged, then we get a positive value. So let's go through this, and either way you do it, you can do a vector or a p orbital. So let's look at this first one here. An identity gives us a 1. A C2 through the z-axis gives us a -1, right? This just is going to twist by 180 degrees. So gray goes into white, or negative into positive. The XZ axis is the one that is in the plane of the orbital. And if it's in the plane of the orbital stays put. So that's a +1. But the one in the plane of the board is going to be the opposite. So this is going to be a -1. So we have just generated a symmetry pattern for this X translation. Let's move on to the Y. So I have the p orbital here along the y-axis. Again, identity is going to be 1, and the C2 is going to be a -1. But now the YZ or the XZ axis is perpendicular, so that's going to switch the two. So here we get a -1, and then this one is going to be +1. If we do the same thing for the Z-axis, so we're here now, we get a +1, a +1, a +1, and a +1, right? Because it is along the Z-axis, we rotate, plus a positive stays positive, and same with those 2 mirror planes, and so this is completely symmetrical. Now what we're going to do is this vector here, it's a moving vector. It's not even a vector because it's not straight. I don't know what to call it. It's a rotation. It's a moving rotation. And so if the direction of this rotation, let's make it go clockwise, if we perform the symmetry operation and it goes counterclockwise, then that's anti-symmetrical. So that's simple. So doing E is going to be 1. Doing C2 is also going to be 1 because we're doing it around in the same direction. And the 2 mirror planes are going to reverse that vector. So this is going to be a -1 and a -1. So we now have generated a character table for the C2V point group. So I've added all of the missing rotations here. We did the X, the Y, the Z, and then the RZ, and so and I've added in the binaries and the squares. So again, we have the IR and here Raman. And so over here we also get a symbol called the Mulliken symbol. It in itself has, it reflects the symmetry pattern. Like if something is A or B1, that's with respect to the principal C2. And so you see here a 1 and a 1 if it's A, if you see a -1 and a -1 if it's C2. And so those mean something as well. I have a summary slide later. So what we're simply going to do is we're going to rearrange it. We're going to put this up and we're going to put this down. And so this is what it would look like from you. And so one of these symmetry patterns here is sometimes referred to the irreducible representation. In the next lecture we're going to look at reducible representation. And yes, I know this is a lot of information, and where am I going with this? Just bear with me. We're going to be when we're done with it, you're going to be looking at how many IR and Raman bands and what symmetry patterns are responsible for those bands, and that can help us with our infrared spectroscopy. So anyway, back to this character table. As I said, every point group is going to have all of its operations listed, and then we have the translations and rotations, which are IR active, and the binaries and squares, which are Raman active. And so here in this case, all the bands that are deducted from what we're about to do will be IR and Raman active. So these Mulliken symbols, just so you know, sometimes there's A and B, which would refer to the principal axes, and then 1 and 2, A1 or A2, is with respect to the C2 or the sigma V. Again, 1 is symmetrical, 2 is anti-symmetrical. G and U, you'll see, those are from German gerade und ungerade, jawohl. So those are with respect to the inversion center, and then we have primes and double primes, and that would be about the sigma H. And then there's some other symbols, and just so you know, it has meaning. You will not need to memorize that, but it's just interesting to know. Here are a couple of examples of what's in the handout. The handout has every single character table for all of the point groups that we have. And so here is the C and H group. The two examples are C2H and C3H. And as I said, the little Mulliken symbol here, first of all, the A is with respect to the principal axes, and the G and U are with respect to the inversion center. So little g means symmetrical with respect to the inversion center. And the C3H, we have primes and double primes, and so that would be the respect to the horizontal mirror plane. So either way, there's a lot of information here, and I'll show you what to do with it in the next lecture. The next example is of a tetrahedron, and the only reason I'm showing this to you is because I got very tenacious when I learned this as an undergrad. I played around with the character table. I looked up a tetrahedron, which was methane. Perfect methane is in the TD point group, and I was just curious if I can find all of the symmetry operations. And so there are 8 C3s and 3 C2s and 6 S4s and 6 sigma Ds, and so that's just a lot, and these are difficult to find, and I got really hung up on the mirror planes, and I think I spent a solid 6 hours building and molecules and looking at shapes and trying to find all 6 mirror planes. You know, you can find one that's in the plane of the board, and then there's one that goes this way too. It's not that hard to find, but that's just 2 of them. Where are the other ones? And so it really helps to take that tetrahedron and put it into a box, and like this, where you have the carbons on opposite ends, and then so you have this cube here, and of course we have 6 faces. But if you cut if you look at a mirror plane through here and here, obviously that is through 2 faces, and so the 6 mirror planes are through 3 of the faces here, like that. And it took me about 30 seconds to show you where they are, but it took me at least 6 hours to figure this out. So sometimes you can get stuck in a loop looking for these symmetry elements. I had a blast doing it. I encourage you to do the same, but blah blah blah, right? So in the next lecture we are going to tackle the reducible representations and apply a very simple mathematical summation to the character table to deduct these. For example, in water, those 3 vibrations, which symmetry patterns are responsible, and whether or not they are IR and Raman active.